Okay, this video is going to be about number systems and representing numbers in various ways. Okay, so when we talk about the origins of keeping track of numbers, keeping track of things numerically, let's say we have a grouping of items here that we want to count, right? And we're just going to represent those as dots here, like this. Okay. Now, if I want to communicate with someone about how many items I have, say we're at a market and I want to tell somebody how many of these things I have for sale, right? I need some concise way of representing that, right? So one of the first forms of doing this was just hash marks, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so one of the first ways to represent counting things is 0 is just no marks, and we have a hash marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Let's see, it was 17, right? Let's see, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yeah. Okay, so in this particular number system, we only have one set of characters that we can use, and that is the hash. That's our alphabet for using numbers, or for illustrating numbers. We have one hash mark that we can either use or not use. All right. This is not the most efficient way of writing numbers, because as you can see, when the numbers get very, very large, like how would I represent a number in the thousands, for example, this is a good solution for counting small things, but when you get up to larger numbers, it becomes difficult. All right. Now, it's important to understand that the idea of a number is an abstract concept. We can write down what that number is, and we're trying to communicate an idea of a number, but we're just using symbols to communicate that. All right. So there's lots of different symbols that can represent a particular number. For example, Roman numerals. All right. If we go through and write out the Roman numerals, 1 is an I, 2 is II, 3 is III, and then 4 is IV. Okay, the V stands for 5, and so 5 is V. So this is 1 minus 5, or 5 minus the 1. Anything on the left, if it's a lower value number, you subtract it from 5. Okay, so underneath here I'll write them in the classical form that we're used to. In the decimal, the Arabic number systems: 1, 2, 3, 4, and 5. Okay, so these 5 numbers in hash marks are 1, 2, 3, 4, and 5. So it's important to recognize everything in this column here still represents the number 5. It's just a different way of communicating that number. Okay, so you have to have a system. What system are we using to communicate our numbers? Right? So Roman numerals were good because they would give us a concept of large numbers. So if we look at this chart here, we have the Roman numerals. So the letter I, the character I, represents the value of 1, and you can add those together. And then V represents the value of 5, X represents the value of 10, L is 50, C is 100, D is 500. Okay, so let's write 444 in Roman numerals. All right, so that would be over here. 444. This is in Arabic. This is on our base 10 standard numbering system. and we'll pull over the Roman numerals that we're going to need. So we're going to need a CD, so that's going to be, the D is 500, and we need to subtract 100 from that to get 400. Right? So we'll do a CD. We'll go ahead and write that first. CD. Alright, and then we need 40, so that's going to be an XL. L is 50, and we need to subtract 10 from that, so XL. So X, and then L, and then we have IV. Okay, so this is a much better way of representing larger numbers than hash marks. Okay, now the problem with this is there's a fair amount of subtraction and addition involved when you just look at this number, and it becomes problematic when we try to do arithmetic operations, right? We're used to a number system in which we can just add the columns. That doesn't necessarily work here because these digits here represent one value. There's two digits to represent one value 4. These two digits represent 40, and these two digits represent 400, and then you add them together. Okay, so while this is a big improvement over the hash system, it still has problems. It's hard to do arithmetic operations, even just basic addition and subtraction. Okay, so an improvement upon that system is the Arabic number system, and that's the number system that we're used to. That's base 10. Okay, so if we look at the alphabet here for the Roman numerals, so the alphabet, by that I mean the characters you're allowed to use to make Roman numerals. All right, this is our alphabet: I, V, X, L, C, D, M. Alright, so we've got I, V, X, L, C, D, and M. Okay, so those are the characters you can use to combine to represent numbers. Now remember, numbers are an abstract concept. We're just trying to represent them on paper. Okay, but numbers exist outside of their representation. We're just using symbols to try to convey an idea. Okay, so for a base 10 number system, what is our alphabet? Okay, so we have the character 0. We have a representation for 0, which is new. Okay, the hash mark system did not have a representation of 0. 0 was just no marks. Same with Roman numerals. There was no marks. And also, in those systems, you don't have a concept of negative numbers. Okay, so immediately we get a benefit moving over to the Arabic number system. So what is our alphabet? It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is our alphabet for the Arabic number system. There are 10 of these digits. Okay, probably because we have 10 fingers if you include our thumbs, right? So we see that there's 10 because if you go 1, 2, 3, 4, 5, 6, 7, 8, 9, that's obviously 9, and then 0 would be the 10th digit. Okay, now what are the benefits of this? Once we get up to past all of the numbers in our alphabet, so we start at 0 and we go 1, 2, on all the way up to 9, what do we do? Well, this is considered the units place. Alright, so in this place we are representing single numeric values. In the decimal system, we just add a 1 to the left of that number. Okay, so now after 9 we have a 10. Okay, so we have 0 units and 1 tens place. Okay, this can continue when we go 11, 12, 13, and then on down until we get to 19. Now again we are out of digits. Alright, so this has to go back to a 0, but to the left side we increase this by 1. And this is 20. Alright, so we're all familiar with this. This is very common. We're most familiar with the Arabic decimal system. Alright, what happens when we run out of digits again? So we go, we're in the 90s, we go 98, 99, oops, 99, and we can we can increase this, but we're out of digits here, so this has to become a 0, and this is where our carry the 1 comes in, and or up here we carry the 1, and then this is now a 10. Okay, so now we're out of digits on the tens place. Alright, so we add 1 here. So now a 1 in this third position means 100. Okay, and this continues with 998, 999. The same process occurs. Alright, so we have this becomes a 0, we add 1, that becomes a 0, we add 1, that becomes a 0, we add 1, and now this position stands for 1,000. If I have a 2 here, it stands for 2,000. Alright, so if we look at what's happening, we have to kind of analyze what's happening as we move into different number systems. We're all familiar with it, but we don't really think about exactly what's going on. So let's write out some digits. Okay, so this is our units place. We are in base 10. Okay, so this digit represents 10 to the 0 power. Anything to the 0 power equals 1. Alright, so 10 to the 0 power is 1. This is the ones place or units place. Okay, this is 10 to the first power. Okay, 10 to the first power is just 10, so that means this is the tens place. This is 10 to the second power. This is 10 to the third power. This is 10 to the fourth power. And 10 to the fifth power. Okay, so we're not used to thinking of the places like this, but that's actually what's happening. Alright, so this is the ones place. This is the tens place. This is the 100s place. This is the 1000s place. And this is the 10,000s place. And this is the 100,000s place. Okay, so if I put a 1 here, let's just fill in some numbers. 1, 3, 7, 0, 5, 2. Okay, so we know this number to be 137,052. Alright, so what is that saying in terms of these digits? Okay, that's saying we have 1 times 100,000. We have 100,000, and then we're going to add to that 3 times 10,000 because we have 3 10,000 items. Right? We have a 3 in the 10,000s place, and then we're going to add to that 7 thousands, so 7 times 1,000. Then we're going to add to that 0 times 1,000. Or 100. We have a 0 in the 100 place. Okay, so 0 plus 5 times 10 plus 2 times the ones place. Okay, and when you add all these up, you get this number. But again, the numbers can be represented in different ways. So when we talk about different bases, which we're going to talk about next, we do the same exact thing as that we've done in base 10. All right, we have individual placeholders, but the value of those placeholders is different. Okay, so let's talk about base 8 or octal. So in octal, you see we have oct, which we know is an 8. Right? So this is base 8. And what is our alphabet in base 8? We have 0, 1, 2, all the way up to 7. Okay, so 1, 2, 3, 4, 5, 6, 7. There's 7 of those, obviously, and then if you count 0, that's 8. So whatever base we're in, we're talking about how many how many characters are in our numeric alphabet that we can use to construct these numbers. All right, so when I write out a number in base 8, it's similar to what we just did in base 10. So I have the places, right? So we have 3 places here. This is 8 to the 0 power instead of 10 to the 0 power. But anything to the 0 power is a 1, right? So that's a units place. Then we have 8 to the 2nd power. So 8 times 8 is 64. Then 8 to the 3rd power and 8 to the 4th power. Okay? So 8 times 64, 2 times 64 is 128. 2 times that is 256, and 2 times that is 512. So that's the 512's place. Okay. Oops, I skipped one. This is, let's go. 8 to the 1st power is just the 8's place. There we go. That's better. 8 squared is 64. And then 8 to the 3rd is 512. Okay, as you see, as you add placeholders to the left, you're just increasing the power of the base. Alright, so this is 8 to the 0, 8 to the 1st, 2, 3, 4, 5, 6, 7, on and on and on it goes. This allows us to create bigger and bigger numbers without really changing the system. One of the problems with the Roman numeral system is you had to come up with additional characters. Okay, we instead just add a number to the left, and that means a larger value. Okay, so this system can, in theory, create numbers of any size. All right. So if we have in base 8, if we have the number 1, 0, 3, 3. All right. What do we do? We're used to this number in base 10 representing 1033, but we're in base 8, so this is different. Okay. We can never have a number in base 8 that is 8, 8, 8, 8 or 9999 because that is outside of our alphabet. Those characters do not exist in base 8. So 8s and 9s are not available. Okay. So this is 1 times 512, so we have one of those. And then we need to add 0 times 64. 0 times 64. Then we need to add 3 times 8. And then 3 times 1. Okay, so 1 times 512 is 512, plus 0 times anything is 0, plus 3 times 8 is 24, plus 3 times 1 is 3. Okay, so 512 plus 24 is 536, plus 3 is 539. So this whole thing equals 539, right? Okay. So this equals 539. Now this number is written in base 10. Okay. So when we have fewer digits in our alphabet, so we only have 8, and in base 10 we have 10 digits in our alphabet. When we have fewer digits, we see that the number tends to be longer in terms of the number of digits we have to use to represent it. Here we could represent it in 3 digits, but these are base 10 digits. Over here it took 4 digits in base 8. The smaller your alphabet, the more digits you're going to need to represent numbers, but you can still represent all of the numbers. Alright, so let's go to binary. Now, the whole point of this is we need to be able to communicate with computers. Alright, you've probably heard that computers speak binary. This is base 2. Okay. There's a reason that you've heard that computers speak binary, and that's because of electronic circuits. We can represent a 1 and a 0 electronically. Okay. So by supplying a voltage, a positive voltage, so if you have a pin, I can store a positive voltage on that, and then if I have another electric pin, I can store 0 voltage on that. Right? If I have a positive voltage, that's like the number 1. If I have 0 voltage, that's like the number 0. Okay, so what is our alphabet for this number, or for this number system? It's binary. Okay, so it's base 2. Base 2 means that there are 2, or I said 2 and wrote 2. Base 2 means that there are 2 characters that we can use to construct the numbers. Alright, so whatever the base is, that's the number of characters in your alphabet. And these could be anything. Alright, we're using 0 and 1 because we're used to it, but we could also use, square and triangle. That could be our alphabet if we wanted. And we could still represent a number. Alright, so I'm going to represent a number in binary. So to start off, we'll just start counting. Alright, so we go 0, like in most of our number systems, most of the Arabic style number systems, and then we go 1, and we increase on this units digit until we run out of our alphabet characters. Okay, so we've gone 0 and 1, and almost immediately we've run out. Alright, so what do? Well, just like in base 10, when we get to 9, it rolls over back to 0. So this goes back to 0, and now we add a 1 over here. Alright, and then we keep increasing the units place. Alright, but now almost immediately again we're out of characters. Alright, so we make this a 0, and we add 1 here. Uh-oh, we're out of characters over here too. So we add a 0, and now we're at 3 digits. Now on this side I'm going to write the base 10 version of these numbers. This is 0, 1, 2, 3, and 4. Now you see in base 10 we have 10 digits and I'm sorry, 10 characters to use, right? And so we're still on our units digit. In binary we have far fewer characters to use, and so we've already expanded our digits out. This in base 10 is 100. In base 2 it's only the number 4. Right, so we can keep counting. So we have 0, 1, 0, 1, and now we're out of digits in the units place again. So this becomes a 0, this becomes a 1, and this is a 1. And then we add a 1 again, and we have 1, 1, 1. Right, out of characters, that's a 0, 0, 0, 1. Alright, so this is 4, 5, 6, 7, 8. Okay, so in binary, 1, 0, 0, 0 is the number 8. And let's keep counting a little bit longer. We have 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Did I miss one? So this is 8. This should be 9, 10, 11, 12, 13, 14, and 15. Okay, Now if we look here at just this column of these numbers, there's a pattern that you should recognize. Yeah. Sorry, I'm not good with this tool yet. Alright, we see 0, 1, 0, 1, 0, 1, 0, 1, right? There's a pattern. Now if we look over here, we see a similar pattern. It's different. We have 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, right? And then if we look over here even further, there's an implied 0 in front of each one of these. Okay, so we have 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, and then with the implied zeros all the way through here, you've got 8 zeros and then 8 ones. Okay, so that pattern is has to do with our base. Okay, so again, we write out our digits and we have 2 to the 0 power, 2 to the first power, 2 to the second power, and 2 to the third power. Alright, anything to the 0 power is 1, so that's the units place. This is the 2's place. This is the 4's place. 2 times 2 is 4. 2 times 2 times 2, that's 2 to the third, is 8. Okay, so when we look at this number, let's look at 13. We have 1, 1, 0, 1. Okay, so what that means is we have 1 times 8, so we have 1 in the 8's place, plus 1 times 4, plus 0 times 2, we have no 2's, plus 1 times 1. Okay, when we add these up, this is 8, plus 4 is 12, no 2's, and then 12 plus 1 is 13. Okay, so this whole thing is 13 in base 10. And as we see, that's the number we have here. Okay, so bases, you can represent numbers any number of ways. Numbers are an abstract concept. It's very important that you recognize that. All right, we can have negative binary numbers. We can have 0 represented in binary. All right, any number we can write out with the decimal number system, we can write out in octal, or we can write out in base 2. All right, so let's do one more number system that comes up quite often in computer science. We have hexadecimal. Okay, so this is base 16. Alright, what is the alphabet in hexadecimal? Okay, we've got 0, 1, 2. Now we have 16 characters, so that's more than we have in base 10, right? So we're going to use all of the base 10 characters. We're going to go all the way up to 8 and then 9. So 0 through 9, right, that's going to be 10 characters, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 is obviously 9, plus the 0 is 10. Okay, but we need more characters. We're supposed to have 16 characters. So what can we use? The standard is to use letters. So we have A, B, C. So this is, we have 10 at 9. This is 11, 12, 13, 14 is a D, and 15 E, and the 16th character is an F. Okay, the 10th character is a 9. Remember, it starts at 0. Okay, so the actual 10th character is 1 less than that, because the first character is 0, the second character is 1, third character is 2, right? So the 16th character, F, actually represents the base 10 number of 15. Alright, so let's do some counting. Alright, so we've got a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, not 10 in hexadecimal. That's the A, B, C, D, E, and F. Now, in hexadecimal, we have finally run out of these characters. Alright, so what do? We have to add a new digit. Okay, so we have 2 digits now, and we put a 1 here, and we start over. 0, 11, 12. But this isn't actually 12, it's just 1, 2. We're representing numbers in hexadecimal. Okay, so a 1 over here actually represents the number 16. This is the 16th place. In hexadecimal, let's put the places out here again, and I recommend you do this as you fill out these numbers. So we have 4 places. This is 16 to the 0 power, which is the ones place. Alright, 16 to the first power is the 16s place. 16 squared and 16 to the third. So just like all of the other bases, every digit represents the base, and the rightmost digit is the base to the power 0, and then you increment that power, right, as we go left. The next digit is the base to the first power, the next digit is the base to the second, third, fourth, and as we extend on out, that power just increases. Alright, so here this isn't the number 12 and 13 that we're used to. There's a 16 here. This is 116 plus 3 units, 3 ones. So this in hexadecimal is actually 19 in base 10. Alright, so let's represent this. Let's keep counting. 14, 1, 5, 1, 6, 1, 7, 1, 8, and 1, 9. And now we're out of our decimal characters, but that's okay because in base 16 we have these additional characters. So we're not done with this place yet. We go 1A, 1B, 1C, 1D, and 1E, and 1F. Right? Now we increment to 2. Okay, remember this is 2 16s. So this is 32 plus 1. So this one is 33 in base 10. Alright, and this goes all the way down to 2F. We're out of characters at F. It's the last one. Right? So now we increment again. Alright? So we increment 3 like that, and we keep going until we get to, 9E, 9F. Now in this 16's place, we're out of the decimal characters, but again, we have all of these to work with still. Okay, so F rolls back over to 0. I'm sorry, there should be a 2 0 here and 3 0. So F rolls back over to 0, and what comes after the 9? A. So this is A0, A1, A2, and this goes all the way down to A, E, and then A, F. Then it rolls over to B0, B1, B2, all the way down to BE and BF. This keeps going until you get to C0, down to CF, D0, DF, E0 to EF. Now this is where it gets interesting. We are at F0, finally to FF. Okay, so FF, we have F16, right? So F represents the number, the decimal number 15, right? This is the decimal 0, decimal number 0, decimal number 1, 2, 3, 4, 5, 6, 7, 8, 9. A represents decimal 11, 12, 13, 14. See, oh, I'm sorry, A is 10, 11, 12, 13, 14, 15. Right? So F is 15, so that means we have F, we have 15 16s, and then we have 15 ones. Okay? So F, F. Okay, so this is the decimal number 15. 15. So what this becomes then is 15 times the 16s place plus 15 times 1. Okay, you add that up, and that is the decimal value of FF. Now once we are out of these characters and all of these digits, it's just like any of the other number systems. Okay, we add an extra digit, and so now we simply have a 1 here, 0, 0. Alright, so this is 16 squared, 16 to the first place, and 16 to the 0 power. Okay, so that is the basics of the number systems. They all operate the same way, right? So we all of the Arabic ones do. We know decimal, that's what we're most familiar with. We went over octal and binary, and now base 10, or base 16, known as hexadecimal. Okay, so in one of the upcoming videos we'll go over converting, right? And you already saw basically in all of the number systems, this is how you convert to base 10, right? It's the value of the digit, so each one of these digits in our alphabet here has a value. This is 0, 1, 2, 3, 4, A is 10, 11, 12, 13, 14, 15. So the value of the individual digit times the value of the place that it's in. The place that it's in is, this is the 16 squareds place. So one of these, we have 1 16 squared, we have 0 16 to the first, and we have 0 16 to the zeros. Alright, so that's how you convert all of these number systems to decimal. So that's enough for one video.